To officially kick off SCSP's AI Expo for National Competitiveness programming on the center stage, please join me in welcoming Dr. Kim Budil, Director of Lawrence Livermore National Laboratory, and Dr. Brian Spears, Director of the Artificial Intelligence Institutional Initiative at Lawrence Livermore National Laboratory. They will be having a joint discussion on Lawrence Livermore's groundbreaking work on a series of emerging technology areas. Thank you, Kim and Brian.
Thank you so much. And thanks for joining us here today to learn a little bit about AI. So we're super excited and honored to be able to be here with this great exchange fostered by Ash Carter, looking over the horizon and new and emerging technologies.
Yeah, and thanks also to our STSP partners. They've been fantastic working with Lawrence Livermore since their inception, and we really appreciate having the stage to share with you guys and just the fantastic conversation they've started for us today.
So today we have two missions. We'd like to share a little bit about how the Department of Energy and the National Nuclear Security Administration are driving innovation in AI today. And then we'd like to look a little bit to the future and how transformational AI and world-class science are going to position us for U.S. national security and competitiveness. So we're going to look at this through the lens of an example. So you may have heard of our laboratory, Lawrence Livermore National Lab. We were in the news in recent years for the achievement of fusion ignition in the laboratory. So this was a long journey for the laboratory, 60 years of R&D, patient public investment in this incredibly important science. So early in the history of our laboratory, scientists wanted to be able to study the process of fusion ignition in the laboratory. And at that point in time, the only places where these conditions were achieved were in thermonuclear weapons and in astrophysical objects like the sun. So a researcher at Livermore had this idea that a new technology that had just been invented, a laser, might be able to produce the conditions that would allow us to compress a very small pellet filled with fusion fuel to those conditions in the laboratory and open the opportunity for us to study that science in detail. So thus began a long journey. The original prediction was it would take about 1,000 joules of laser energy to create those conditions. So we used the laser to create an X-ray bath. We shine the laser into a small gold can. It creates a uniform bath of X-rays that bathe the outside of a capsule that's about 2 millimeters in diameter. Little capsules made out of diamond, and it's filled with fusion fuel, deuterium and tritium, isotopes of hydrogen. And the trick is quite simple. You need to implode that capsule fast enough, at a high enough velocity to get it to high temperatures and densities, and then hold it together long enough for the fusion reactions to take over and ignite. So what happened? We built our 1,000-joule laser, and then an ever-increasingly more powerful series of lasers over the decades. In the 2010s, we were able to use the Natural Ignition Facility, a 2 million-joule laser, to continue this research. What we learned over the arc of time was an incredible amount of innovation in science, technology, and engineering was required to achieve those conditions. And on December 5th, 2022, we finally achieved the goal of producing more fusion energy in an experiment than the laser energy required to drive it. 3 megajoules of fusion energy for 2 megajoules of laser energy. And again, we started with a 1,000-joule prediction. It took 2 million joules to get to that point. Along the way, we invented whole new areas of technology, from extreme ultraviolet lithography to deformable mirrors that are the key to the laser guide star that's revolutionized ground-based astronomy. And this impact on our national security missions can't be underestimated. This is part of the Stockpile Stewardship Program, and it's part of what allows us to sustain the safety, security, and effectiveness of our nation's nuclear deterrent without underground nuclear testing, significantly contributing to global stability and security.
Right, and so those innovations that Kim talked about don't just stop with the national security missions themselves, but they go all the way down to the foundations of what we can achieve scientifically, both traditional science and AI. To give you a feeling of just how fantastic what we have done is, let's start with something that I still find hard to believe. We take X-ray images of something that is at temperatures and densities greater than that in our own sun. It lasts for about 100 trillionths of a second. It's smaller than the diameter of your hair. And we take pictures of it at 100 billion frames per second. So we can actually capture pictures of what's happening inside the little star we create in the laboratory. But we don't just stop with the traditional science. We also push that forward to AI. So as we were moving toward this ignition moment, the experiments were becoming clear that this was possible. The traditional design simulations that we use, very high fidelity physics simulations, were pointing that way. And we unleashed a new model, one that was driven by AI in the background. And after this lined up, on the night before the ignition event, I sent an email to our esteemed director, Kim, and said, hey, for the first time in my 18-year career, the most likely outcome, as predicted by this high-quality AI model, is that this thing is going to ignite. So we can look forward to that. And the next morning, lo and behold, that's what happened. So what did we actually do? We used high-performance computing from the Department of Energy, hundreds of thousands of simulations. We coupled those to the high-precision experimental data, like that 100 billion frames per second frame rate, and we glued them together with an AI model. And that AI model understands the theory the way that the world should be, but it makes predictions that are accurate and precise according to the way the experiments actually are. It's why we had real confidence in what we were doing, together with our other approaches to that model. So that progress that we've made is a clear arc from our missions that we need in our scientific spaces, to the computing that we use to predict it, to the AI that we use to glue it all together and move us into a new direction, looking forward to the things that we can do next.
And AI and computing are really underwriting all of our national security missions. So we're a multi-program national security laboratory, and we support, in addition to our nation's nuclear deterrent, nuclear threat reduction, arms control, counterterrorism, counterproliferation, non-proliferation missions. We also support biosecurity, chemical weapons reductions, conventional support to the Department of Defense, and a wide range of other mission spaces. So AI is clearly an enabler for all of these different spaces. But why is the DOE working in all these areas? Well, if you look at what's happened in high-performance computing over the last 3 decades, that revolution in the use of high-performance computers for multi-physics modeling and simulation has really been driven by the Department of Energy National Laboratories, taking computing from a useful tool to an essential tool for science, technology, and national security.
Right. So it's really useful for all of our missions, and it's actually prepared us in 4 essential ways that allow us to lead for national security, and they also allow us to lead for AI. The first of those is in our computing capability. Across our DOE, we have the world's most powerful scientific computers. They're produced and made up of tens of thousands of GPUs. That's the currency with which we do compute in AI these days. I just walked last week the floor where we're having the El Capitan supercomputer installed. It's being built and finished right now with well over 30,000 GPUs that we can put together to do precision scientific computing. That's simulations at the micro scale for what happens in conditions that we produce on Earth, like those inside the sun. But it's also fantastic for the threaded and repetitive communications and computing that we do for AI. So that's the first pillar, which is the computing. The second one that we've been prepared for by our missions like Ignition, but that's made us ready for AI, is in models. We have the best physics codes on the planet, and we also have world-class large models in AI. Those AI models include language models, like you're familiar with from GPT and those that are in the news, but also specialized architectures for science, ones that speak not the grammar of English, but the grammar of chemistry or the grammar of physics. So that's computing and it's models. The third pillar is data. I mentioned we have things like X-ray cameras that take 100 billion frame per second images. That data is an incredible resource for training these models, not just language. We've used the internet to build text models. Now we have to use the DOE resources, where we have the largest physical databases in the world, to build new models for science and for the nation. And then the final piece that we have is our incredibly compelling applications. So Kim's mentioned a number of applications: the stockpile, bio issues, challenges across advanced manufacturing. Those issues touch not only our national security, but they also touch our national competitiveness. They have prepared us for what we're going to do today, but they allow us to look into the future as well.
So the Department of Energy National Lab System was created in the wake of the Manhattan Project to ensure that the country always had a cadre of experts with incredible tools and capabilities to enable them to meet the challenges of the day. Our job is to look over the horizon, not to wait for things to emerge that need time and attention, but to always be pushing ourselves to be at the frontiers of science and technology. And AI is certainly that today. Each of the labs has unique capabilities and the ability to use AI to achieve incredible promise across our mission space. For us in the National Security Labs, we've been applying it, as I said, quite broadly, but I'd like to give you one example that's related to our biosecurity programs. If you heard the Honorable Liz Sherwood-Randall this morning, she talked about the growing threat of the convergence of biotechnology and advanced computing and tools like AI. So at our laboratory, we're working on a program where we're using high-performance computing and AI to revolutionize the way we design drugs and therapeutics. The idea is quite simple. Computing is now at a large enough scale that we can manage the complexity of biology and begin to design biomolecules for specific targets. So we've been working on a project to design antibodies. This was called into use during the COVID-19 pandemic. As new variants of COVID emerged, existing antibody technologies would not work effectively against the new emerging variants. So our team undertook an effort to redesign those antibodies to meet this challenge on a very fast timescale. We were able to redesign antibodies to meet a new emerging variant of COVID with 2 weeks of computing. Actually, the long pole in the tent for getting those therapeutics into the clinic was the testing that was required by the company that eventually built the molecules and put them into the clinic. But the promise is there. The ability to take timelines for drug development from decades to months or perhaps shorter.
Right, that's an incredibly compelling example. The bio story is motivating. There's more promise. We think of another 4 key pillars of the way that we can use this to transform our national security missions. The first is discovery of molecules. Kim gave a really compelling vignette on the discovery. It's also the design phase, where we understand how to build things that take advantage of new materials, but we use AI agents to navigate enormously complex design spaces that I would love to do as a designer, but I simply can't as a human. So those AI agents enable us to do that. We have another pillar, which is in manufacturing, where we use AI to do self-driving in our manufacturing procedures. That means we can potentially print a defect when we use direct-write 3D printing, recognize that with our physics model and an AI agent in real time, decide how to correct that, and then the next pass seconds later, print the anti-defect so that the part works as it's supposed to without having to start over or be failed. That's the manufacturing pillar. And finally, we use this in our surveillance applications. We watch systems, we watch our production capabilities, we monitor data, places where theory is not available to say how things should act. We have models that can consolidate and synthesize that information and help us predict when things will fail before they fail so that we make sure they never do. I would encourage you also, if you're interested at all in the manufacturing story and the self-driving, we have a wonderful booth here today for DOE, and there will be an example on a self-driving laboratory made small, a little sidekick system that actually does the self-driving that we're interested in for DOE. So go by the booth and take a look at that. That's the promise. There's lots that we can do in the world that is just really exciting, but it does not come without peril. So peril in the AI space, as we look over the horizon, comes in 3 flavors. The first flavor is that's produced by adversaries. Whenever there's a model that's useful to us, there is someone out there that wants to break it. So adversarial AI and the fragility of those models is something that we at DOE are paying very careful attention to. The second threat comes from dual use. Models that are very great at discovering drugs, like proteins that help interrupt pathways so that disease can't propagate, are also very good at interrupting pathways that we would like not to turn off for reasons that could be damaging. So we just heard from the Carter Exchange as well, from Liz Sherwood-Randall, that there's a concern about this not only by nation-state actors, but also by independent and terrorist organizations. We have to pay attention to the peril. The third thing that we have to look to as well is the notion of scale. We have watched in the world as this last year, a few months ago, our partners at Meta purchased 600,000 GPUs. I told you a story about a wonderful computer that has more than 30,000. Their purchase of 600,000 is probably about $10 to $15 billion. That's the cost of an aircraft carrier, and the United States has 11 of those. So we're now in a world where non-nation state actors are moving amounts of money for compute just for models in order to influence the AI world and what's going on. That, against the backdrop of the previous threats of actors who have ill intentions or trying to break models, is something that has to give us pause. And to look over the horizon, as Kim said, we've got to be experts at that. We have to understand what we have to do. To do that, we need a nation-scale effort in AI, and we've got to move fast.
So what Brian said is really important. There are a lot of players in this space, and they're all going to play important roles. For the Department of Energy, our job is to be that public-facing research program, to be operating in the public interest, and to be considering always the national security implications and the broader safety implications of AI for the public at large. But we work in close partnership with industry and always have. Over the decades of our creation of this ecosystem of high-performance computing, we've built deep and enduring relationships with our partners in industry. And today, those will serve us well, along with our partners in academia, our international partners, to help us achieve the benefits of this technology while protecting against the potential perils. As Brian mentioned, the Department of Energy is organizing their efforts around a new initiative called FAST, Frontiers in AI for Science and Security Technology. The idea is to harness the broad range of capabilities across the DOE national labs in science, in energy, and in national security, building on this foundation of computing capability to really accelerate the public-facing program in AI. We really believe that the DOE labs have a foundational role to play here in bringing this technology to the fore and achieving the benefits that we believe are possible for our many important missions.
That's right. So I told you a small story about how we're prepared in 4 pillars. So you won't be surprised that when we think about a nation-scale initiative that DOE is going to lead for our national security and competitiveness, that those same 4 pillars are going to play. So in our FAST effort, we're thinking about it in 4 ways. The need at nation scale to curate data, to build out models, to have compute that we can drive that with, and to focus that on critical national security applications. When we talk about these 4 things, one thing that has to be clear is that we do it at tremendous scale. We're looking at a world where the competition is potentially operating at hundreds of thousands of GPUs, and we have to, for the nation, have a capability to stare over that horizon and understand what works. The lessons from the wonderful things that have been done in industry is that scale matters. Pushing to trillion parameter models, pushing to tens of thousands and hundreds of thousands of GPUs brings differences that we cannot get otherwise, and the country has absolutely got to have that. We need that not only for our national security capabilities, but also for our general national competitiveness. And as Kim said, we're not looking to compete with industry. We have incredible partnerships where we're working to co-design technologies that will work for the future. We've learned through our preparation that the wonderful off-the-shelf capabilities that we have from GPT and Claude and other models work fantastically, but not out of the box for our science. That effort has got to be co-designed right up against the mission spaces where we know what the challenges look like. Remember, we want models that speak not the grammar of English, but the grammar of chemistry and physics. So as we push to this nation-scale effort, we will engage with our industry partners in order to push that forward. And also for the members of the audience who are here from academia, as there are a few, we need you as well. We're going to work together to build out the most robust pipelines for student engagement to help build out a workforce for the US. It's called for in the AIEO, and the DOE is tasked directly to work on that, and we're pushing very hard. We also have the challenge of reinvigorating academic careers. Our academic colleagues and professors do not have access to hundreds of thousands of GPUs or tens of thousands, but we do. And we're going to work together to make sure that they can build us the science workforce that we need to get our missions done for the future.
That's a really important point, Brian. This is really a partnership-focused effort. There are always going to be more people, more ideas, more tools, more technologies outside the boundaries of the laboratories than inside. We try to create specialized capabilities at scale to really enable a different kind of research. The national labs were built on the idea of multidisciplinary team science, so we can bring together large multidisciplinary teams of experts to help be a focal point for an effort that broadly draws on expertise across all of the sectors that we've described. So DOE, with its missions in science, in energy, and in national security, is a critical player in this national scale effort to take AI forward. And in order for the US to sustain our national security and be competitive in this environment, we really need to lean in and move fast. Now, we've all worked with the government before. Moving fast has not always been our preferred gear. But I think you'll see incredible excitement and enthusiasm from our colleagues across the government, across many agencies, to really accelerate our efforts in this arena. It's incredibly important that we be out in front and leading in this arena. This is going to transform everything. We're already seeing that access to tools like AI, data science, high-performance computing is transforming all the disciplines of science and technology that we work with, breaking down boundaries and leading to important areas of convergence, as we described in the example of bio. The DOE labs stand ready to help lead this transformation and to bring our capabilities to this revolution, exciting revolution in AI, and ensure we get the benefits, achieve the promise, and guard against the potential peril. So with that, I'd like to thank you for your time and attention.
Good.